So in the beginning, I recommend you, if you are interested about in this subject, a little bit more detail and a more comprehensive overview and about this topic. I recommend you go to this textbook by Oker. The name is Ecological Models and Data in R. And I recommend for today's class, I recommend you to read chapter 4, Probability and Stochastic Distribution for Ecological Modeling, and chapter 6, Likelihood and all that. And then, in the beginning, I will talk about what is random variable. A random variable is a numerical measure of the outcome from the probability experiment. So its value is determined by chance. Random variable are denoted using the letter, such as the bigger case X. Okay. And for the random variable, you may already learn it in week 2. But I'm going to review the idea because this is really related to the maximum likelihood method. So here is a very simple example about a random variable. So here has a question. This question is an experimental, is a probability experiment. 你认为台湾该以什么名称参与 WHA? So here are the options. Here are the outcome of this experimental test. For example, some people will answer 中华民国. Some people answer Taiwan. So all these value, this name are random variable. Because if you ask some random people on the street and then ask them to pick up this name, they will give you a different one, right? Different people may give you different one. So then each outcome has its probability. So in this case, X can represent name. Name can represent by X. So name, we also call it X, random variable. But if you just write it in the Chinese, this is pretty long, right? It's too long. So in order to make this simple, we can use X equal to 1 to represent 中华民国. Use X equal to 2 to represent Taiwan. Okay? So in this case, this is a discrete random variable, right? Because the outcome is 1, 2, 3, 4, 5, 6, 7, 8, right? So go back to here again. A random variable is a numerical measure, right? From the outcome from a probability experiment. So this is a probability experiment. We use the numerical measure, right, to quantify this. So here I'm going to talk about what is discrete and versus the continuous random variable. A discrete random variable is a random variable that has the values that has either a finite number of possible value or a countable number of possible value. Here I give some example. For example, students' grade level. It can be, for example, A plus, or A minus, B. So these are the, discrete label. And the number of heads when flipping 3 coins. So the number of the heads when we are flipping 3 coins, how many heads we have in total. These are the discrete random variable. A continuous random variable is a random variable that has an infinite number of possible outcomes that is not countable, right? For example, the height of the students in the class. These are not countable. These are height is a continuous number is a continuous number, right? 165.25 centimeter, 180.51 centimeter, so on. Right? You can have more number after the decimal point. It's a continuous variable. Weight of student in the class or time it takes to get to school. Okay. So then here we are going to talk about probability distribution. So a probability distribution provides a possible value of the random variable and their corresponding probability. So this is called a probability distribution. A probability distribution can be in the form of a table, a graph, or a mathematical formula. Okay? So in this case, here has the probability, and here has the distribution. In this case, this outcome has the highest probability, right? And this outcome has the lowest probability. So, a probability distribution provides a possible value of the random variable and their corresponding probability, right? So in that WHA case, the probability distribution can be described by a graph or a table or a formula, right? In here it's described by a graph. This bar, higher bar means higher probability, right? Described by a graph. So probability distribution are generally divided into two classes, right? As I mentioned, we have random variable can divide into discrete and continuous. So the probability distribution can have discrete probability distribution and continuous probability distribution. Here is the discrete probability distribution in detail. So for example, a coin toss, we can have the head or tail. So if we are flipping the coin 10 times, we can have a probability distribution of the total number of heads up, right? Or the weather, raining or not raining, within 1 week, how many days in total in this week we are going to have a raining day? Total number is 3, or total number is 5. Minimum is 1, minimum is 0, maximum is 7. Right? What is the probability? Roll a dice. So, in general, the set of possible outcomes is discrete, such as a coin toss or roll a dice, can be encoded by discrete list of probabilities of the outcomes. So for the discrete random variable, we use the name called probability mass function to describe the probability of each discrete outcome. Here is the probability mass function. We use probability mass function for discrete variable. A probability mass function is a function that gives the probability that a discrete random variable is exactly equal to some value. So in here, the smaller case p means this is discrete variable, and we use for the PMF, okay? And then x is a random variable. X is the outcome. Bigger case means this variable is a random variable. This x can equal to, for example, 0 or equal to 1. These are discrete variables, right? And then what is the probability? And we call this function a PMF. So the table below shows the probability distribution for random variable x, and where in this case x represents the outcome of a coin toss. For example, this is the bottom, this is the head. As we know, a coin is equal for two sides. And here is we represent the probability distribution for the discrete variable case, PMF, we describe by here it's a table, here it's a graph, okay? Talking about the discrete random variable and the PMF, I'm going to introduce a important distribution called the Bernoulli distribution. In the Bernoulli distribution, here are some example. For example, a captured fish either has a tag or doesn't have a tag. A sampled fish either is female or male in general, okay? A fishing set either bycatch a shark or doesn't bycatch a shark, okay? So, in such kind of the probability experiment, we call it a Bernoulli tribe. In the Bernoulli tribe, we can have a random variable x with two different outcomes. One is success, one is fail. You can also think this is head, this is bottom, okay? So the P is called the probability of the success. 1 minus P is called the probability of fail. And it can describe by this PMF. If we are doing many Bernoulli trial and combine them together, and it becomes a binomial distribution, okay? Binomial distribution. It also used for the discrete variable. The discrete probability distribution with the parameters n. N means the how many number of trial you did. P is the probability of success. Of the number of success in the sequence of n independent experiments, each has a yes or no question. So here I give you the example. For example, a scientist sample 100 female fishes. If the probability of spawning is 0.4 per fish, what is the probability of sample 20 as spawning females? Okay? If you already know, based on the literature, you know, in this regional area, this ocean, you sampling, the probability of maturing is 0.4 per fish. And then what happens if you sample 100 fish, and then 28 is spawning? And what is the probability of this? Second case, if a 100 fishing operation was done by a fisherman one day, based on the previous research report, bycatching shark in such kind of fishery is 0.1 per operation, the probability. What is the probability of bycatching shark? 53 times in 1,000 fishing operation. Okay? So let's take a look at the binomial distribution, PMF, in detail. This is the PMF for the binomial distribution. As I say, P, smaller p is for discrete variable. Bigger case is the random variable, X. M is your outcome. In this case, M means the number of success, or number of bycatching shark, number of maturing, number of observing spawning females. Okay? N is the total number of trial. So then this PMF can describe by this formula. what is this here? Here is called n choose m. It's the number of the combination can be formed from n item, taking at m at a time, okay? So here tell you the combination, and here tell you the probability of success and probability of fail, and how many times for each. How many times for each, okay? So if we put this into the real number, then we can get the value. If we plot the value, we can have this graph, okay? So in this case, this is a probability experiment. We already know n, which is total number of trial, and we already know p, the probability of success. And here tell us the n, number of success. So number of success is a random variable. You have success 0 time, 1 time, 5 time, okay? And many times, and probability becomes lower. So it forms a discrete probability distribution. Each outcome is a discrete label, right? 0, 1, 2, 3. You can also call it A, B, C, D. So let's look at this example. So in this case, we have the parameters for this probability mass function of the binomial distribution. So one of the parameters is n. Second parameter is p. The number m is a random variable. We can have the outcome for this random variable as the value of 0 or 1 or 2 or blah, blah, blah. We can calculate the PMF probability mass. We can calculate the probability for each random outcome. In this case, in Excel, we use this function called binomdist. It means binomial distribution. Okay? So, what is here? What is this? This is mean we are going to do a hand calculation, by ourselves. So as I told you, the binomial distribution, PMF can express in this formula, right? So we are going to spell out this factorial term. So here is the factorial term. Factorial term is written in here. And here is the probability term here. Probability term. Number of the success and number of fail term here. So we can multiply the factorial term and the probability term, these two together, then we can have the probability 2. Okay, so these two numbers is the same. These two numbers is the same. Then we can plot the probability and the outcome together, then we can get this figure. Okay? So here I just show you how to do yourself, how to do in hand calculation. If you already know a PMF function, okay? So this can apply to other probability distribution. if you know a PMF function or a PDF function, and then you know the parameter value, you can plug in the value of the parameter and do the calculation by yourself. Then you can understand, okay, what is the random variable value and what is its corresponding probability or probability density. Okay. And how about doing in R, not Excel? Okay, so same. In this case, it will become simpler. We have the N, total number of trials. P is the probability of success. We want to know the probability when the outcome of this random variable is from 0 to 20, right? So we can use D binom. M, as I say, means the random variable X. No, random variable M. N is the total number of trials. P is the probability of success. Right, so this gives you the exactly result. So in R, you can do in this way. It's called D binom. In Excel, it's called binom dist. Okay, same idea. All right. But in some case, this factorial term may not be computable because there's some problem called a numeric overflow. So in such case, we can use the log probability. We can use the log probability. So as I mentioned, the PMF of binomial distribution looks like this, right? So we can take a log. When this part take a log, it becomes here, this one. Oh no, this part take a log, become this one, right? And then the first part take a log, become this one. And this factorial term, we can further do the separation into the summation. So put all this together, it becomes like this. So the log probability of the binomial distribution PMF is this equation. So we can calculate this one first and then put its potential outside. Then it becomes the original scale. And why we want to do this so complicated? Because in some cases, there is a numeric overflow in the computer. You cannot directly calculate the probability for the binomial distribution. In example 12.2, I'm going to show you the example, okay? So here is the same. It's our first example. But in here, I'm going to show you the second example. So we are using the same distribution, binom dist. And the P right now is, P is the same, is 0.25. However, the total number of trials is right now increased to 180. So because we have 180 of trial, we may have 168 or 170 or up to 180 of total number of success. So here is the Excel built-in calculation if we want to calculate the probability for the binomial distribution. Here is no problem. But what if we want to do the hand calculation by ourselves? In here, we can see a problem. If we want to do the hand calculation, first part, we need to come up with the factorial term, right? Like the example 1, we just exactly put the same formula for the factorial term. But then this part is overflowing, right? We cannot have the result because number is too big. Number is too big. Second term is okay. The probability is the multiplication of these two terms. So we cannot have the value here. This is what I call a numerical overflow, when n is very big. How to avoid this case? We can take a log. We can take a log. Okay? We can take a log using this formula. So do the first one, do the second one, third one, and put all these together. So this is the log probability. Then do the exponential back. Then we can have the probability for the binomial distribution when m value is equal to 170. Right? This m value is 170. So these two are the same. All right. So from this case, we know, in Excel, they already take care of this numerical overflow problem. But if you want to do by yourself, sometimes you have encountered such kind of problem, take a log and do the exponential back, okay? All right. So we have finished the discrete random variable. Right now, let's talk about a continuous random variable. So the continuous variable in here, this example, the bigger case, x from 0 to 1, okay? It means there are infinity of potential observed value of x with the range of what is possible, okay? So here is a question. The probability of x, of this x equal to 0.7. What is the probability? Because this is a continuous random variable, right? So in this range from 0 to 1, every number has the same probability. So define its probability, we call it P. I want to ask you a question. Does this range from 0 to 1 contain more than this number, this total number of value inside? The answer is yes. Yes, okay? Contain more than this value of number total inside, within this range. So if this is the case, then the probability of P exactly equal to 0.7 should be smaller than this value, right? Should be. Because within this range, there are so many numbers, right? Does this range contain more than this number, total number of value inside? I think so. The answer is yes. So when x is equal exactly to 0.7, what is the probability? Very slow, very small, right? So actually, within this range, there are an infinity of the potential observed value of x. So actually, the probability of observe a random variable with the value of x equal to 0.7 is actually 0. It's actually 0. With an infinity of possibility, the probability of any particular value would be infinitely small. Okay? So if the probability is 0, what can I do? Right? If it's 0, you tell me, you introduce me the PMF first, and then you tell me for each value, you can observe its probability for the discrete variable. But right now, you tell me in the continuous variable, when the value is equal, when the outcome is equal to a particular value, the probability is infinitely small. So I'm going to talk about this in detail, okay? Continuous random variable. Coin toss in this case is discrete because only 2 outcomes. But continuous variable, there are many outcomes within this range, right? Many continuous values. So what can we do? How do we describe this? How do we use the probability distribution to describe the possible value of a random variable and their corresponding probability? Right? Because as I have told you in the discrete variable, each possible value of a random variable and their outcome is 0. Their probability is 0. How can we do this? Here is the solution. Instead, to examine the literal probability for a continuous variable, we use the PDF called the probability density. We don't use probability. We use the probability density, okay? We quantify an area under a PDF. So I'm going to talk about the density concept in here. So how to, in this case, this is a sword, okay? This is a sword made by metal, very heavy, okay? Very heavy. I want to know this sword is in good quality or not. Is it in good quality or not? It means the metal density is good or not, very even or not. Or some part is very weak, or some part is very strong. And weak and strong is related to the density, right? The metal density. If the whole sword made in a very good condition, then the density probably is very even, okay? So how to evaluate the quality of this sword? The mass, we call 质量, right? At any point is close to 0. Why? Because I'm going to cut this sword into very small thin pieces. So if I use the machine to cut a very small pieces, so this is very small pieces because it's just very, very small. So the mass is almost equal to 0, right? And then I calculate the density I'm going to weight by a machine, right? and then calculate the density of this wall. So I can come up with this value, right? So the density, how to calculate density? We cut this range, right? So the mass for this range divided by the size, okay? Then we can come up the density. Then we measure the density for each location. Then we can have this density profile of this wall. Then we can know, here is not, quality is not so good. Here quality is very good, okay? Similar idea can be used in probability, okay? Similar idea can be used for probability. So this is called a probability density function. This red curve is the density. And here is the probability, right? The probability from when x is equal to smaller case x, and then until x is equal to smaller x plus the delta x. So within this small range, what is the total, what is the probability within this small range? And what is the size of this range? So this probability divided by this size. And when this size, the change of the size is very small, right? We can have the PDF. This PDF means for each very small point, each particular point, the corresponding probability density, okay? Density. So here is a relationship between the PDF and the probability. So for the PDF, for the probability, right, we can calculate, we can integrate, what is the probability mean? Probability means the area under the PDF curve, okay? So this area means the probability. Because we integrate out the x term, delta x term, right? So the probability for this blue polygon is this area minus this area, right? So you integrate this PDF from here to B, and then minus from here to A, right? These two integration do the differences, then you can have the probability in this area. So the relationship between the PDF and the probability. So this is the definition of PDF. This is the definition of probability, okay? So probability, you can have the PDF multiply delta x. Approximate. So in this case, I'm going to show you how to do the density, probability density by hand calculation, okay? So here is the length of the tuna fish. As we know, the length is a continuous variable, right? And then in this case, I'm going to show you 3 examples. We have a data, we have a length data, and then we are going to use the bin size of 10 to calculate the density for each size class. And then the bin size of the length interval range from 10 to 5 and until to very small bin. So this very small bin is equal to this idea when the delta x is become very small, right? And this phi is the density. All right. So we are going to calculate the density for a very, very small interval and see what happens. Density for a bigger interval, density for a moderate small interval, density for very small interval. All right. So before I start it, I'm going to generate lots of number of the size data, okay? So I generate the random variable from a normal distribution with the mean 300, standard deviation of 30 centimeter. So these are the random variable I generate. And then I'm going to define the minimum length interval and the maximum length interval and the bin for the length class. Here, I do a histogram for this size data. Right, this is the histogram of the size data. So what is this? This is the density. So within each size class, the corresponding density, okay? And what does this curve mean? This is the probability density based on the normal assumption. Okay, this is the probability density based on the normal assumption. In the binomial case I show you, if you want to calculate the probability distribution, you can use the by d norm. Well, no, you can use the d binom. For the normal case, you can use the d norm. So d means the density, okay? Here, you can do it by your hand. You can do it by your hand, okay? So, you calculate the probability for until the first bin, and then the probability until the second bin. And then you minus, you use the first bin, minus the size, the area of first one minus the second one. So here is the area of second one minus first one, and then divide by the delta x, then you can come out the PDF. Okay? So here I'm going to make it more beautiful. So the bin median bin is this one. Divided by 2. Okay, let's try this. So here I monitor the bin and the corresponding probability density. Okay? And we can plot this one too. So should be the same. Right? This is circle. This circle is the same. So let's increase the bin. Let's reduce the bin interval. This is 10, right? I'm going to do 0.1. So first one. Because the bin right now is very small, right? So the histogram looks like this. And this is the built-in PDF from the definition, right? So of course this one is the built-in one is very small. So as I told you, when the bin is very small, it becomes toward to the continuous case, right? And we do the hand calculation here. We don't use the built-in function. We do by our hand. Let's see what happens. I'm going to change the color. More easier to read. So here is we do by our hand. So this one basically is equal to this one, okay? All right, so right now we understand the definition of the PDF. We understand the definition of probability density. How to calculate density, right? You calculate the probability within a small range of area first. And then you divide this probability by the size of this area. You become the density. Because for a continuous variable, for a particular value, its corresponding probability is very small. It's almost equal to 0. So we cannot compare the relative importance of different values because those probabilities are all very small. Instead of doing this, we use the probability density, okay? So the built-in one, the built-in curve, I told you in this example, right? D norm. This is done by using this formula. So this is the formula for the probability density function of a normal distribution, okay? For the probability density function, we don't use P anymore, we use F. We use the smaller case F. Smaller case F. X, bigger case X is still same. It's a random variable. Smaller case X is the outcome of this random variable. For each particular outcome, we can describe by this red curve. This red curve can derive from this formula. Parameter mu is the average. Parameter sigma is the standard deviation. Okay? if you do the integration for this PDF curve, you can have the result 1, okay? You can have the CDF. CDF is you do the integration for each, until each particular range, okay? And then when you do the all integration from the minus infinity to positive infinity, the whole area probability is equal to 1. But if you just do it from very small value until the very large value and do the profile, then PDF will look like this, a logistic looking, okay? All right. Let's take a break for 10 minutes. So let's start again for the following section. And here I'm going to talk about the likelihood concept. So in the earlier part, I talked about probability distribution, the definition of the probability mass function for the discrete variable, and the definition of probability density function for the continuous variable, and how to do the calculation by your hand, and how to do it in Excel, and how to do it in R with some built-in function. And here, I'm going to talk about the likelihood concept. So what is likelihood? Here, some description we can. 同学，那个门帮我关起来好不好？谢谢。With any model of a process, there will be a parameter set for which the model predictions are obviously inconsistent with the available data, and others are likely. So for some process, right, you can observe the data, and then you can have a model with the parameter to come up some prediction. When you compare the prediction with your observed data, then by changing the parameter, for that parameter, or even some parameter, the prediction are more close to the data. For some parameter, the prediction are not close to the data. So for the cases when the results are close to the data, we say those parameters are more likely. And for the cases when the parameter, the prediction are not close to each other, they are unlikely. So conversely, there will be other parameter set that produce prediction closely consistent with the data, and these we feel are far more likely. So what is the maximum likelihood method are attempting to do? Maximum likelihood methods are attempting to find the parameter set that is most likely. And how to define the likelihood? We use, for the discrete variable, we use the PMF to define the likelihood. For the continuous variable, we use the PDF to define the likelihood. Okay. So here I'm going to talk about probability and likelihood for the discrete variable. This side is the probability. Okay. If I flip a fair coin 10 times, what is the probability of landing heads up every time? Right? So given the fixed parameter, a fair coin, we already know the parameter. P is 0.5, right? So what is the probability of different outcomes, right? So the probability of heads up is 0.5. The probability of bottom is 0.52, right? And if we flip 10 times, what is heads up 1 time, heads up 2 times, right? We can know about it. We can know the probability. If we know the fixed parameter. But in the likelihood concept, it's different. If I flip a coin 10 times and obtain 10 heads, what is the likelihood that the coin is fair? Given the data, I want to know, is this parameter likely or not likely? For the parameter cases, given the parameter, I want to know the probability of each possible outcome. Okay? So, given a fixed outcome is the data, what is the likelihood of different parameter values? For the probabilities, all the probability sum up together is equal to 1. Likelihood do not add up to 1, okay? So likelihood means the hypothesis. So likelihood is given on what? Given on the fixed outcome of data, right? What is the likelihood of different parameters? Different parameters also represent what? Different hypotheses, okay? Different hypotheses. So hypothesis or parameter value are compared using the likelihood. This parameter is likely or not likely? Based on what? Based on the observed data, right? So higher means more likely, lower means unlikely. So continuous variable, this one is discrete variable. This one is continuous variable, okay? So for a continuous variable, probability is what? As I mentioned before, right? Probability is the area under the PDF function curve, right? So what is in this case, this example, what is the probability that x is larger than 5 and small and equal than 10, given a normal distribution with the mu 13, sigma 4, right? What is the probability? Within this range, right? What is the probability that value of x is within this range for a normal distribution? The answer is 1, right? But let's talk about likelihood. What is the likelihood that mu equal to 13, sigma equal to 4, if you observe a value of x equal to 14, right? So, given the observed outcome 14, right? How likely for the parameter is equal to 13 and 4? We can see how likely. This is the likelihood, right? We use the PDS, we use the probability density to represent how likely this one compared to how likely this one. So given this fixed outcome, the result tells us the greater one is more likely, because given this outcome, the likelihood is more than 0.08. But for this one, it's very small. So this means this parameter is more likely than this one. Okay? So this is the likelihood. This is the probability. They are all talking about probability or likelihood, but just what is fixed is different. Okay? Don't confuse. All right. So talk about notation, probability or probability density. But we use this P. So even the parameters, okay? We know this coin is fair. Okay, so parameters 0.5, right? What is the probability of different outcome? So you can also write it this way. P is the parameter, Y is the data. Data is the represent outcome. You can have multiple outcomes, right? For the discrete variable, you use the probability. For the continuous variable, you use the density. All right. Likelihood, flip around, okay? Use L. Right now it's given by your data, right? So here you can say different hypotheses or different parameters, right? So likelihood given by Y is data. Here is the parameter. Okay? What is the likelihood of given hypothesis about a variety of parameter value P, given that you observe a fixed value of the data Y? All right? Okay. So, talk about the likelihood. Even the fixed observed, even the observed data, what is the likelihood of different theta? Right. You use P and F for the discrete variable, so smaller case P, right? And then this is the likelihood, right? This is equal to, it's same. If given your X, you want to come up with the likelihood of theta, but actually the calculation is even if theta, you do your X. It's the same. Calculation is the same, but the thinking is different. But when you do the calculation, you still use the P and F for discrete variable, right? For the continuous variable, you want to calculate the likelihood even X is equal, data is equal to X, right? What is the likelihood of theta? But in the calculation, it's the same if given your theta, right? What is the probability of this outcome? All right. And here is the PTF function. This is the PNF function, right? So discrete variable likelihood calculation, continuous variable likelihood calculation. All right. So we are going to look at a case to do the likelihood method for the binomial distribution. So in this case, you are starting the birth rate in a C-alter population with the 30 number of females, okay? 30 individuals. During a study season, each female either give a birth or doesn't give a birth. So, one scientist go to the ocean, right? They have the data. 10 females give birth, 20 do not. Okay? So, what we are interested in is about the parameter, right? So, what is the p-value? P-value is the probability of birth. Probability of birth is p is equal to 0.3, 0.4, or 0.7. Which one is more likely when you observe this kind of data? Can you tell me what is the population, rate of birth in this case? All right. So we are going to do the exercise here. So we have the parameter set up in here, 30, 30, 30, right? This is fixed. What we want to know is about the p-value, 0.3, 0.5, or 0.7, okay? So given these two parameters, we have the likelihood for each possible outcome, right? We can have the likelihood for each possible outcome. But right now, what we have is this one, right? 10. Because 10 female give birth, 20 do not. So this is our data. This one is our data, right? So given the observed data, 10, this is the likelihood for different parameters. The likelihood for the parameter is equal to 0.3. It's about 0.14. The likelihood for the parameter P is equal to 0.7. It's very small. It's less than 0.00003. Okay? So the figure here is what? It's the value of the birth number. Here is the data. The current data is this one, 10. Different colors means different parameter assumption and its corresponding probability. So, sorry, here is the color is wrong. This color is green color. So this one should change to the green color. This is blue.
Professor, can you wear your microphone?
Okay. So this one is P equal to 0.3. This one is P equal to 0.5. This one is equal to P 0.7. Okay? The legend is wrong. All right. So we can see where is the data. Our data is here, right? 10 female giving birth. So the likelihood for P equal to 3 is very high. The likelihood for P equal to 0.4 is lower. The likelihood for P equal to 0.7 is almost 0. So in this case, given this data, we can know the P equal to 0.3 is highly likely. Okay? So we can calculate the maximum likelihood estimation. Okay? How to do it? So we do a profile for p-value and calculate its likelihood value.
So we do a profile from 0 to 1 and do a 2 decimal point increase from 0.01, 0.02 until 1. Then we plot the value of P and the value of the likelihood. We can have the result of this graph. Which value of birth rate, the likelihood is the maximum? It's when the birth rate is equal to 0.33, right? 0.33. The likelihood is highest. All right. So 0.333, the likelihood is highest. So this p-value is the maximum likelihood estimate in this case. Okay? So maximum likelihood estimation, we call maximum likelihood estimate, MLE, or P is equal to 0.33. Likelihood, birth rate, using the binomial PMF and setting birth rate P to different value between 0 and 1 in steps of 0.01, we gain a set of likelihood, and then we plot it. We can come up with this MLE value. What if we have multiple observations? If the observation and data points are independent, then we can multiply the likelihoods together. If we have multiple observed outcome, Y1, Y2, Y3, then the likelihoods should multiply together. Likelihood of Y1 multiply likelihood of Y2 multiply likelihood of Y3. Okay? Because they are independent. In this case, when smaller value multiply together, then you will have more smaller value. When you have many observations and all multiply together, then your total likelihood will become very, very small. Then you will have some problem when you want to do the numerical optimization. For example, the minimization or the maximization. So we don't directly handle the original likelihood. Instead, we use the log likelihood. Take the advantage of the mass property. When we take the log of the likelihood, right, the multiplication can become additive. So the likelihood, the log likelihood of observation 1 right now is add up with the log likelihood of the observation 2 and the log likelihood of the third term, right? Become sum up. So let's see the second case, multiple observation. So the sea otter study has been extended to 3 field seasons based on the same number of sample size for each season. Okay? So in these 3 seasons, right now the new data is 10, 20, and 30 female gave birth respectively. Okay? So we want to know about the p-value again. For the first case, we only have 1 data point. This second case, we have 3 data points. Assuming independent between years, what is the overall likelihood that P is equal to 0.3 compared to P is equal to 0.5 or 0.7? So here we can have the PMF for P equal to 0.3 for this data set, this second data set, third data set. Another alternative hypothesis is P equal to 0.5, right? And the probability for the 3 data point. Again, another alternative hypothesis, the probability for the 3 data point. As I say, if we have multiple observations, the probability should multiply altogether, right? So this is the total likelihood. Very small value, right? On the other hand, we can calculate the log likelihood and sum up all those log likelihood together. This is the log likelihood. But not exactly. Here it's called N et al. Et al. N is what is the N? What is the meaning of N? N is mean the negative log likelihood. We do the summation of the log likelihood and then we put a negative sign. We change the sign only, so it's called a negative log likelihood. All right. In here, this red box is called an MLE estimate. Here, just the 3 different alternative hypotheses, but this is the exactly solution for these 3 data points. P is equal to 0.46. As you can see, the total likelihood is what? Very small, right? No, it's higher, very high, very likelihood is higher, means this assumption is more likely, right? So likelihood is very high, it's bigger than these 3. The negative log likelihood is what? Smaller. So when you look at the log likelihood, you look at the likelihood, you want a higher value. If you want to look at the negative log likelihood, you want to have a smaller value. All right. So this is the example. We have the data here, and then the corresponding probability. So we can calculate the total likelihood, just do the product. This product means these 3 numbers multiplied together. All right. And then we can have the negative log likelihood. Here is the joint likelihood, right? For different p-value. Again, like the case 1, we are going to do a profile for p-value from 0 to 1 with a small value of increment 0.01 in sequence. This is the likelihood, or you can call the probability for each data point. This is the joined one. Then we do a profile. This blue curve is the negative log likelihood. This purple curve, dash purple curve, this one, is the likelihood, total likelihood. So the maximum is where? 0.46, right? When you take a look of the maximum value. Similarly, if you take a look of the negative log likelihood, where is the minimum? Minimum is around the same, 0.64. All right. So likelihood versus negative log likelihood. Minimization, maximization, minimization. Okay? Let's talk about the maximum likelihood estimator of the population parameter C.0. What we are interested in the many example real cases, we don't know about the population parameter. But we want to know about the population parameter. For example, what is the parameter of like average body length of Taiwanese people, right? We don't know about this true value of the population, but we can have sample. We can have sample to get information of data, right? We can have sample to have data, and we can have assumption. We can have assumption about the population value, right? We can have assumption about the Taiwanese people body length. We can have assumption of different body length value, right? Given the observed data, we can come up how likely of each different assumption. This is the idea of the MLE, right? The maximum likelihood estimate, this one with the head, this is the estimate value, is from this function. This function is what we want to do. We want to get the theta from the space of theta, from this bigger theta space, right? And how to find the solution is matched with the condition. What condition? When the likelihood is highest. When the likelihood is highest. So here is the likelihood equation. We want to find the likelihood is the highest. How to find the highest likelihood? You can use the relative. You can take the first relative. So for example, here is the likelihood, and here is the value of different theta estimate, right? So we can know the likelihood is highest in here. At this point here, the derivative is equal to 0. It's equal to 0. A good estimate of unknown parameter theta 0 will be the value of theta that maximizes the likelihood given the data we observe. In order to maximize the function, we need to do the differentiate the likelihood function respect to theta, okay? So let's take a look about the log likelihood function and the likelihood function for a continuous variable. For example, a normal distribution, okay? So for a normal distribution with the two parameter mu and sigma, the log likelihood function and the likelihood function are this, okay? So here I show you the log likelihood function. Log likelihood function is you take a log of the likelihood function. What is the likelihood function for normal distribution? It's this one. This one. And we take a log of this one. Okay? It becomes here. Nth means if you have the multiple observation. Okay? And here is you sum up all the observations together. So this equation here is give you the total likelihood. Okay, not the likelihood for each data point. It's the total likelihood. Once we know the total likelihood for a normal, once we know the log likelihood for a normal distribution, we can do the differentiation with respect to mu, with respect to sigma. The maximum occurs when the derivative is equal to 0, right? So under these two conditions, when the derivative is equal to 0, this part is the result after we take the first order of derivative, right? So solving these two equations, we can get the mu value under the maximum likelihood estimate. So the mu value actually is just the average value. And this one is the sigma value. This one is the sigma value. All right. And the unbiased MLE for variance actually is n minus 1, not n. Okay? So the log likelihood function and the likelihood equation for the binomial distribution. This one is the likelihood function for the binomial distribution. This one is the log likelihood function for the binomial distribution. Okay? So for the log likelihood function, let's do the derivative with respect to p. When we take the derivative, this is the result, right? The maximum occurs at the derivative equal to 0. So if we make this equation equal to 0, we will have the solution of p equal to m divided by n. So this is the maximum likelihood estimation value. So for that C-alter case, right? 10 giving birth, total number is 30. We know this is follow a binomial distribution. So the p-value is 10 divided by 30, 0.33. This is the case, okay? The p-value. The number of success divided by the total number of trial, okay? So I have introduced you about the likelihood, the probability, the total likelihood, the total negative log likelihood, how to find the maximum likelihood estimate value for a discrete variable and for a continuous variable. I show you the example by using a normal distribution and by using an example of binomial distribution. Here I'm going to show you about the likelihood for a linear regression. A linear regression. So let us assume that each level y y subscript I is a normal distributed with the mean value at here and the variance at this value. OK？ 同学，我们休息10分钟好了。Let's take a break and then I go to the regression part, which is the final part. Yeah. And then we go the homework. Yeah. OK， 同学上课哦。So last week, the homework, you do the least square estimation, right? So you want to minimize the residual sum of square, right? So you calculate the residual square for each observation and sum up together, come up a residual sum of square and do the minimization. For the least square estimation, actually it follows what? It follows a normal distribution. You assume for each data point, it follows a normal assumption. It's not explicit, it's implicitly assume follow a normal distribution. But in the maximum likelihood world, we are specific, have an assumption about the distribution. In this case, for the linear regression, in here we specific assume each observation follow a normal assumption. So this is the mean value, right? So here is the mean value plus what? Error term. Your error term is an error around 0 with the magnitude of sigma square. This is the error. So prediction plus the error term become observation. What you want to do is you want to find out the theta, right? You want to know the theta. Okay. What is this xi and the upper subscript upper script T mean. This is the matrix notation because we are handling multiple observation. So we use the matrix notation for the linear regression. Xi is a vector of the x value, but we do the transform, so become a raw vector. A raw vector multiply a column vector. So each cells multiply the corresponding cell and sum up together, right? So this is matrix notation. So what is the likelihood in this case? As I said, the likelihood and the probability is one of the other. So in this case, we calculate the likelihood value for each observation. So this is the PDF for normal distribution, right? PDF. We have multiple observations from I equal to 1 until n. Because they are all independent observations, when we want to have the total likelihood, we want to multiply all of the likelihood value together. So we put this sign. This sign means multiply together. Okay? Here we just spell out the PDF for normal, right? And this one finally come up to this one. Okay? So these two cartoon plots just tell you what is the likelihood of two different alternative hypotheses. This blue line is one alternative hypothesis for the parameter A and the parameter B. Parameter A means the intercept. Parameter B means the slope, right? This one is another hypothesis for this curve. The points here is our observation. So I'm going to show you the likelihood for each data point, okay? For example, this data point, Y3, this is the value, and this is what? This is the predictive value, Y hat. Okay? So, this is the likelihood given the model is here. Given the model is here, how likely is this observation? How likely? Right? So, not too bad, it's high. When model is here, how likely is this observation? The likelihood is, oh no, this one. This value, the likelihood is very low, right? On the other hand, in this case, for this data point, when the model is this one, right? The likelihood of this observation is higher than here. The likelihood for this observation, given this hypothesis, is still high, right, compared to this case. So, by comparing these two cartoons, we can know this curve is more likely to be true comparing to this curve, because the likelihood of these two data points is lower than the likelihood of these two data points given the assumed hypothesis. So this one is more likely. The likelihood, the maximum likelihood estimation is we want to solve this curve. We want to solve this line. Given the maximum likelihood estimation, the total likelihood, which is the summation of the log likelihood of each data point, will be maximized. Or the negative log likelihood will be the minimum value. Or the total likelihood, which is the multiplication of each likelihood value, all multiplied together is highest. Okay? So maximum likelihood of the linear regression. The maximum likelihood estimate of theta is obtained by taking the derivative of the log likelihood. The goal is to minimize the log, it is to maximum the likelihood of seeing the data y by modifying the parameter. For a simple linear regression, the parameter theta represents intercept A and the slope B, and also the errors, the residual error, which is the sigma square. This is the probability density function, or we can call it the likelihood function for the normal assumption. The log normal likelihood can be represented by this equation. We want to find the maximum value of this derivative, right? So we take the first order of derivative with respect to theta, and this is the result. And then the maximum value occurs when the slope equal to 0, right? And we can do the same thing for sigma square. By solving these two equations, in the end, we can have the maximum likelihood estimate value called theta hat ML is equal to this equation. This is the analytical solution. An analytical solution, okay? We can have the maximum likelihood estimate value for sigma square, which is called sigma hat square ML, is equal to this equation. These two equations is just simply by taking the first order of the derivative and make it to 0 and solve the parameter value for theta and sigma. So let's try the example 12.6. So here is the x value, y value, and the predicted y. Predicted y, we can put some initial value for the curve. The initial value is, where is it? AB. Here, A and the B. Right, this is A. A and the B. So this is the predicted value. This is the error square. As I show you here, we have the analytical solution for theta hat ML and the theta hat square ML. So let's try it. So we first make the x vector first in the matrix form, and we do the transportation, and then we do the X transport multiply X, and come up this 2 by 2 matrix. After do this 2 by 2 matrix, we do the inverse. After do the inverse, we come up this value, X transport multiplied by Y, right? So by the definition, the B value is equal to this term multiply this term, right? This is a 2 by 2 matrix multiply a 2 by 1 matrix. So the result is the 2 by 1, right? 2 by 1. So the result of C dot is A equal to minus 0.32, B is 0.3. This is the solution, okay? So these are the prediction given the A and the V value here. So we plot the predicted Y and the original X. We have this red curve. It matches very well. Of course, this is the analytical solution for a simple linear regression, right? So we can do a simple linear regression within Excel too. Okay, so for example, data analysis, regression, Y value is here, X value is here, output new workbook, right? This is the result from Excel output. So in this table, I already had the same result when I do in Excel. Let's compare the value when we do the Excel data analysis and compare to the analysis we do the hand calculation based on the definition of the maximum likelihood, right? They are the same, right? They are the same. So right now you understand how Excel handle this estimation. They are doing in a maximum likelihood, all right? Same, we can calculate sigma. So the sigma is what? Sigma is based on this definition, okay? And the unbiased estimate for sigma is n divided by 2. No, n minus 2, because we have 2 parameters. This is related to some statistical property. I'm not going to detail, but just tell you, if you just do the derivative, this is bias. You need to minus 2, become unbiased, because you have 2 parameters. Okay? So this is the unbiased one. And this is the, this is a sigma square. So sigma square, this is sigma. So the unbiased sigma is 0.29. Let's take a look at Excel, this one. So the standard error from the Excel calculation is the sigma value. This is the meaning of this value. Okay? So we can do it in the negative log likelihood. So this is the likelihood. We can come up the negative log likelihood. So without the negative sign, under this bracket is the negative, is the log likelihood, and we put the negative sign, become the negative log likelihood. Right? This negative log likelihood can written in this format. Because the 0.5 multiplied log 2 pi is a constant, so this term often is omitted. So in the end, the negative log likelihood become a simple version of format like this equation. So how to solve mu and sigma? We can minimize the sum of the square and the variance, right? For this negative log likelihood, we can minimize this negative log likelihood. So we can do the we can do the maximum likelihood estimation for the linear regression by using the probability density function. Do it by ourselves. In this slide, I show you the analytical solution, right? I'm going to show you the numerical solution by using the maximum likelihood estimation. Here is the XY value. Oh no, sorry. And here is the linear regression. Here is a linear regression model. And we can calculate the likelihood function for each data observation in here, right? So what does this part mean? This is the likelihood. What is the likelihood? Likelihood is just based on the definition of this formula. So the PDF, or we call the likelihood, is written in here. We can calculate the negative log likelihood. We take the log of the likelihood and put a negative sign. And here we do some bookkeeping, right? Some derivative quantity we want to store in the computer program. And then we set up our objective function for our parameter A and the B, right? And we have some initial value for A and the B, and we use the optim like we do in the least square minimization. But in this case right now, we are specifically assign a probability distribution for each data point, okay? So let's run this. So optim do the optimization for multiple times, and in the end, the likelihood is almost same value, right? So then we can have our solution for A and the V. So this is the result of the maximum likelihood estimate. This is the negative log likelihood. OBJ is log likelihood. Yes, so this is the negative log likelihood. Smaller, right? From a bigger value. Initial is small, but jumping around, jump to big, and then jumping around, and then computer continues use the Newton method to solve, and then become asymptotic, small. And this is the parameter value for A and B. So we do a numerical maximum likelihood estimation. Okay? And here I show you is an analytical maximum likelihood estimation. All right. Sometimes we want to understand about the uncertainty of the parameter estimate. For example, the standard error. Standard error is the uncertainty about the parameter estimate value. If we do the estimation many times, then we can have, for example, this average value. We can have many average value, and the standard deviation of this average value is called a standard error. In the maximum likelihood estimation, we can have the variance of the parameter. The variance of the parameter is by taking the second order of the derivative and then do the inverse. Then we can have the variance of the estimation value. For example, in binomial case, we take the second derivative and do the inverse. And this value is the sigma square. And the sigma value is this value. Okay? So the inverse of the second derivative of the log likelihood can give us the information about the variance of the parameter. Here is the example for the variance estimation of the maximum likelihood in the case of the normal example. Okay? So we take the second derivative and then put a negative sign, and then we calculate the expectation of this matrix. This matrix is called a Hessian matrix. The second derivative matrix is called a Hessian matrix. And then we can do the inverse. This inverse matrix is called a curvature matrix. And the value in the diagonal term is the standard error of the parameter. In this case, it's the standard error for A and the standard error for B, standard error for intercept, and the standard error for sigma, for slope. So this is the example of the linear regression. So this is the analytical solution for the linear regression variance estimation based on the maximum likelihood definition. So we take the second derivative and then we come up the expectation and then we do the inverse, and then we can have the analytical solution for the parameter uncertainty. All right. So here, we do the second derivative and then we do the inverse, and then So by definition, it's this one, right? Sigma multiplied by this term for A, and this one is for B. So we can do our hand calculation. This is the sigma. After sigma multiply this, become this term, right? So this is the standard error. And we do the square root, become these two values. Let's compare with the Excel built-in calculation, right? 0.6, 0.039, 0.6, 0.039. These are the same. So this I do the hand calculation based on the property of the maximum likelihood method. I do the second derivative and do hand calculation by the analytical solution. And this is the Excel give me the standard error of the coefficient intercept and the standard error of the coefficient slope. They are the same. All right? So I explain you how to do the uncertainty estimation. Excel example 12.7. It's do the maximum likelihood estimation in Excel. So this is the numerical optimization. In this code, I show you how to do in R. And in here, I show you how to do in Excel. Same idea. You just calculate the likelihood, or you can calculate the negative, or you can calculate the log likelihood, right? And log likelihood can have a simple version. If you want to remove the constant, this is the simple version. So this is the total likelihood, this is the negative log likelihood, this is the negative log likelihood based on the simple version of the formula. We can put some initial value in here. We can use the solver to do the optimization. So we want to minimize our negative log likelihood, right? So it's minimize, choose minimize, not maximize. A and B are two parameters we want to solve. So we do the optimization. So this is the result. Based on what? Based on the maximum likelihood method by assuming normal distribution assumption. Okay? All right. So homework. The Bomber-Lengthy growth function is usually used to describe the body growth in length for many fishes. Okay? So here is the Bomber-Lengthy growth function looks like. LT means the size at ht. So when h is t, what is the size? L infinity is the parameter of this growth equation. K is another parameter for this equation. T0 is another parameter for this equation. So how does this equation look like? So this equation looks like this. L infinity define the maximum size for the fish. T0 define the initial point of this growth curve. K value define how steep of this growth curve. Okay? So I want you to use the Bomber-Lengthy growth curve to describe the growth pattern of one fish, one real case fish in the world. So here is the data. This is the one fish from this paper, 1980s. The fish age and the fish length. Okay, so based on these two data sets, I want you to fit a bomber lengthy growth curve to this growth data. And you have three parameters, L infinity, K, and the T0. I want you to fit this growth curve by using the measure of maximum likelihood. Okay, so for each data point, you need to have a statistical probability distribution assumption. Once you know the probability distribution assumption, you can have what? Likelihood value. I want you to maximize the likelihood value by solving these three parameters. The solution will be you need to find a value that maximizes the total likelihood of the data, okay? But here it's a little bit different. In the class, I only show you the normal distribution. I only show you the binomial distribution, right? But in this homework, I don't want to use the normal distribution. I want to use the log normal distribution, okay? Slightly different version of normal. It's a log normal distribution. So right now the error term is become this, okay? So log normal distribution. This is the PDF for the log normal distribution, okay? PDF. So you can, if you have many observations, this one is the total log likelihood, okay? No, this is the total likelihood. And this one is the negative log likelihood. So please do the homework in R. This is a little bit challenging, but I give you an example of homework in here. In the Excel version. So we can have different value of the parameter. So right now it's not fit, right? Because this is the data, this is the model, totally not fit, okay? So what you need to do is what? You need to calculate the predicted value, the difference square. You need to calculate the total likelihood. So here it's the total likelihood definition, turn 1 and the turn 2 and the all, right? This is the negative log likelihood, turn 1 and the turn 2. So in this case, we want to do what? Objective value is which value? This value, right? This is the negative log likelihood. We want to do maximize or minimize. Minimize, right? Because it's a negative log likelihood. We want to solve these three values, right? Do we want to constrain the solution not to have negative value? No, right? No need. Let's try. Okay, so this is the solution. When L infinity is 60.27, K is 0.32, T0 is very close to 0, we can have this growth curve describe the length and the age data quite well for this fish. Okay? And then I show you a template in here. So all you need to do is you need to write out your likelihood function here and your negative log likelihood function here, and then put together and put into the optim and make the optim works. I show you the example, 2 example on YouTube, how to use the optim with the maximum likelihood. And then also a supplement PDF reading about maximum likelihood programming in R. In this case, it's a normal distribution example. But I think it's very simple. You can modify into log normal. So